Hi, this is Professor Fernandez, and this is video 2 in lesson 17. We are now talking about the fundamental theorem of calculus, which sounds important, and indeed it is. It's one of the most important theorems in calculus. I'm going to do that in the context of example 5.6 from Calculus Simplified. So let me read through the example first, and then we will get to the fundamental theorem when we are in need of it. Zooming in a little bit here, consider f of x equals x on the interval 0 to 5, and let t be inside this interval. Okay, so let's just draw a little graph for ourselves so we know what's going on. We can visualize it. So y equals x, there we go. And then from 0 to 5, so this is x equals 5. This would be 25. Oh, never mind. That would be 5. I was thinking about a different slope function. So that's y equals x. And then t is inside this interval. So t is maybe somewhere over here. All right, so that's all the setup we're given. Part A, show that this. So what is this? Well, on the left-hand side, this is a definite integral. So we talked about the notation for the definite integral in a previous video, the one before this one actually, video 17.1. So if you want to review that, go ahead and check that one out. So show that the definite integral from 0 to t of the function x is equal to t squared over 2. Okay, so let's do that first. What does that mean? All right, so the integral from 0 to t of x dx, that is measuring the area between the graph of y equals x and the x-axis, where x ranges from 0 to t. So here is x ranging from 0 to t, and here is the graph of y equals x. So I'm talking about this area between the graph and the x-axis and ranging from x equals 0 to x equals t. That area is the area, if I pop it out here, of a triangle. The base length of the triangle is t, right? If you imagine t is like 4 or 3, that would be what goes down here, 4 or 3, that's the base length. And the height of the triangle over here is whatever the y value at this point is. But since we're on the function y equals x, and this is x equals t, then the y value is also t. So down here, the height of this triangle is t. And now we're asked basically to find the area of a triangle with base length y and then altitude t. So that area is 1/2 base times height. We know the base is t, we know the height is t, so we get t squared over 2, which is what's up there. So check, did that. Awesome. No fundamental theorem of calculus yet. That is part B. So part B says verify theorem 5.1 in this setting. What is theorem 5.1? Well, let me erase this because we're going to need some space to verify that, and head on over to the right-hand side where we have theorem 5.1. So I'm going to zoom in here. This is the statement of the fundamental theorem of calculus as I put it in Calculus Simplified. So what does it say? It says, suppose that f of x is continuous on the closed interval a to b, okay, and define the function a of t by blah. I'll tell you and give you some insight into that in a minute. Where t is between a and b, could be a, could be b. Then, conclusion, a of t is continuous on a comma b. Pretty cool, because this is a definite integral that is now being made into a continuous function. That's cool. It's also differentiable on the open interval. Hey, so not just continuous, but also differentiable. And we know what its derivative is. It is equal to the f of x function in here, otherwise known as the integrand. So this is one of the reasons why this is the fundamental theorem of calculus. Integration is one of the pillars of calculus, along with differentiation and limits. And differentiation here is one of the other pillars. And this theorem connects both of them. It says if you look at this statement, since a of t is this, a of t is this, okay? It says that the derivative of a of t, d by dt of this, equals the function that is inside here, the integrand. In other words, if I step back and look at what I have written, the derivative of the integral of a function is that function. That's a really simple way to put it. And if you just rewind that and you listen to it in English, the derivative of the integral of a function is the function. It basically tells you that differentiation and integration undo each other. So this was a really great insight in the development of calculus. What was until then thought of as two different branches of the subject, not clear how they interrelate, were intimately related by this theorem. And the insight and the end was that differentiation and integration are in some sense inverse processes. They undo each other. Okay, enough about the fundamental theorem of calculus. Let's verify it for this example up here. So how would I do that? Well, I want to go through and check everything to make sure I can actually use the theorem. So suppose, these are the assumptions right here. So I want to check all that, and then this is a conclusion. I want to verify that this is true, that this is true, and that this is true down here. So I have three things to verify and a bunch of stuff to check. Okay, so suppose f of x is continuous on a comma b. Okay, what is the f of x in this problem? It is x. Question, is y equals x continuous on the interval 0 to t? Yes, it is. Y equals x is continuous on any interval. So check. And then define the function a of t. We're defining a of t by the integral from a. So what is the a in this problem? Well, we have to look at the interval we're dealing with, 0 to 5. So a is a left-hand point. Okay, so integral from a, so left-hand point, over to t, okay, of the function, which is x dx. Okay, sometimes you may see this function called the accumulation function, because as t ranges, if t is 1, you get this area. If t is 2, you get this area. If t is 3, you get this area, right? So the area is kind of accumulating. You may hear that word for this type of definite integral. Okay, so we have defined that function. We're making our way through the fundamental theorem of calculus down here. Then a of t is continuous on AB. That's the first thing we have to verify. All right, at this point you're wondering, how can I possibly verify for this? Well, that was the point of part A, right? We just show that this definite integral equals t squared over 2. So this actually is t squared over 2. So we are verifying that the function t squared over 2 is continuous on a, which was 0, and then b, which was 5. Remember, that's the interval we're using for the problem. So question, is t squared over 2 continuous on 0, 5? Answer, yes it is. Remember all the continuity we talked about. I'm forgetting the video reference in this series, but this is a polynomial, right? It's a quadratic function, and those are continuous everywhere, including, therefore, on this interval 0 to 5. So check. Second, we want a of t. We want to make sure that a of t is differentiable on the open interval. Well, let's have a look at a prime of t. This is a power function, power rule, differentiates it to 2t, get rid of the 2's. A prime of t is t, another polynomial, right? A linear function, continuous everywhere, differentiable everywhere. So, a of t really is differentiable because its derivative exists at every point, including at points between 0 and 5. So a of t is differentiable on the open interval 0 to 5. And then last one, we want to verify, is a prime of t equal to f of t? Okay, well, first of all, we know that a prime of t is t, just calculated that. And what is f of t? Well, let's go back to this problem. And what was the function that we were working with? F of x is x. So f of t is just changing the letter. F of t is t. So we go down here, f of t is t. So t equals t. Verified. All right, so that's the last thing to verify. So zooming out here, we have done all possible checks of the theorem. We verified its hypotheses, we verified its conclusions, and the fundamental theorem of calculus holds for the data given in this problem. Okay, so I'm just going to do a very quick review as usual for the end of the video. Oh, that didn't erase anything. Let's try it again. That is better than nothing. So as a very quick review of this video, the definite integral, which for our purposes so far in the course has been measuring the area between the graph f of x and the x-axis. Again, we're assuming that the graph does not dip below, so we have negative y values. We'll treat that later. So the definite integral that has been measuring that area quantity is this. And the fundamental theorem of calculus down here says, basically, if you change the upper limit so that it is a variable, right, this creates a function. Again, I referred to that earlier as an accumulation function. As t increases or changes, that area increases or changes. Remember the picture I drew with this area turning into this area, turning into that area. And then as a function, you can ask all sorts of things about it. Is it continuous? Is it differentiable? What is its derivative? And the fundamental theorem of calculus tells you, provided you satisfy the hypotheses, yes, it's continuous, yes, it's differentiable, and its derivative is the integrand. So that's FTC. You might, in other sources, know this as FTC Part 1, or maybe some references call it FTC Part 2. By the way, FTC refers to Fundamental Theorem of Calculus, right? I'm not going to use Part 1 and Part 2. I'll just call it the Fundamental Theorem of Calculus. Later on in the video that you can kind of see down here, we will talk about what is sometimes called the other part of this theorem, which some people refer to as the evaluation theorem, and that's what I'll refer to it as. Thanks for watching.